Hey guys, Dr. DeFeo. So, I'm going to give you an example of how I would go about explaining your quiz corrections. One of the key things that I'm going to be looking for is that you have an organized process, that I see equations, that you have the right sig figs, and that you are able to, you don't overlook or the way that you explain the concepts are not too ambiguous. That you don't sort of gloss over certain aspects of it. Okay. So obviously I have a Surface Pro. Some of you guys don't. That's perfectly fine. All you need to do is solve this by hand, take a picture of it, and then if you put it into PowerPoint, as you can see, you're easily able to talk from that. But please make sure that it's legible and readable, that you zoom in, that you can clearly see your handwriting. Okay. So let's give it a try. So the reaction problem number 75 is an interesting problem. It makes you really think hard about how solids are involved in equilibrium expressions. I think you recall from our typical reaction, if we had solids, you would need to figure out the limiting reagent in order to figure out how much at the end of the reaction, how much of the products you have, right? That's the whole goal of that is to do that. So the problem is that as you start reacting 1-to-1 moles of these, right, there is going to be a certain probability that it's going to go in the opposite direction. Okay, and at equilibrium, assuming that you have an excess of these reagents, or at least an excess of one of the reagents, you can be assured that you're still going to have some carbon dioxide left over. Okay, so it's really important to keep that in mind. And the other thing to keep in mind is just because the concentration of the solid will remain constant throughout the reaction, it doesn't mean that the amount of the carbon, so the moles of carbon, you will lose carbon, but the concentration of it remains the same. And that's kind of hard to swallow, but it's very important to keep that in mind. All right, so let's look at this. First step is right off the bat, you can see that when you do your limiting reagent calculations, that you have many more moles of carbon than you have of carbon dioxide. Okay, and so even if, hypothetically speaking, this reaction lied all the way to the right, you would run out of carbon dioxide. Yeah. We know it doesn't go all the way to the right, but it definitely seems like it goes pretty far. So let's take a look and see what's happening. All right, so we'll assume that carbon dioxide is limiting. And now what we're going to want to do is use Pivnert to take and convert the moles into pressure, because it's going to be through the equilibrium expression of the pressure that we're able to figure out the total pressure at equilibrium. So first we figure out the pressure of, let's see, this would be the pressure of carbon dioxide initially. You're going to lose a certain amount of that. A certain amount of pressure is going to decrease. You're going to gain a certain amount of carbon monoxide. Okay, and when we do our we plug these equilibrium equilibrium pressures into the equilibrium expression for pressure, and we get our quadratic equation, and then we plug it into the quadratic equation, we will end up getting 0.677 atmospheres of pressure. And so that's how much carbon monoxide is lost, and twice that amount is how much carbon dioxide is gained. But we also must keep in mind that if we at equilibrium have this much less of carbon dioxide, we also must keep in mind that minus x also means that you're going to lose a certain amount of moles of carbon too. Of course, this is in pressure. Later, I'll show you how we can. Figure out how much carbon was actually consumed. Okay, so taking your initial value of carbon dioxide and subtracting it by X, you end up finding out that you get 0.319 atmospheres of carbon dioxide, and carbon monoxide, you're going to end up getting 1.35 atmospheres. You add them together and you get your total amount of pressure. So I said you can figure out how much carbon solid was used at equilibrium. To do that, you would take your value of X, and you would want to find out how many moles how many moles of gas have been consumed, so that we can figure out how many moles of carbon can be consumed, because there's a 1-to-1 ratio between carbon dioxide and graphite. And when we do that, we end up finding out that we are going to utilize 0.0687 moles of carbon dioxide, and that is the same number of moles of carbon that's consumed. And you find out that really you only use about 5 milligrams or so of carbon solid consumed. Now, why is that important? Well, we were fortunate in the way that the question was asked that we knew right off the bat that carbon dioxide was limiting, okay, because the moles of it were less than the moles of carbon. But as we start tightening down the amount of carbon in this situation, you can have the reverse situation. But this gets a little bit tricky, okay, because in order to find out if carbon will be limiting, you have to ensure that the amount of carbon that you have in the initial reaction is less than the amount of carbon that's consumed. So really, you wouldn't be able to do the second part if you didn't do this beginning part. Okay? But as it turns out, you can see that half a gram of carbon ends up being very less moles of carbon than the moles of carbon dioxide that were reacted at equilibrium. Okay, and so because it was less, we know that the carbon is limiting, and that even though we still have the same initial amount of carbon dioxide, recall that initially we had 0.1011 moles of carbon dioxide. Here we had to convert things to pressures because we didn't know how much carbon was used. Okay, but now we know that we have an excess of carbon dioxide, and so similarly we are going to actually be able to consume all of it. Okay, given that fact that these are the only two gases, the only thing that contribute to the final pressure of these gases, lost my train of thought. Okay, so this problem is actually simplified. You don't have to convert things to pressure down here like you did previously, because we know what X is. Okay, X has to be the moles of carbon. Now, if there was plenty more carbon given the pressure of carbon dioxide, then we should be able to definitely react more than 0.0416. In fact, we should react upwards of 0.0687 moles, but we don't have that. So, we're using the ICE equation, but we're not really using it in the same manner as before. What we're really trying to do is figure out how many moles. We're doing stoichiometry, in fact. Okay, so we have this many moles. This is the amount of, so if you have 0.101 moles of carbon dioxide, you don't have any initially of carbon monoxide. This is how many moles you've used. This is how many moles of carbon monoxide you get. Then you can plug them into the pressures, into ideal gas law, and you're able to get a total pressure of 1.96 atmospheres, which doesn't look like it has the right sig figs. So this looks like it's going to be closer to, I guess, 2 atmospheres. So as it turns out, I had some wrong math here. So at the end of the day, you end up with 1.41 atmospheres. If you're checking at home, you can double check that, but I'm pretty sure that the answer is 1.41 for total pressure. And so the takeaways from this is to keep in mind that even though the concentration of the solid is going to be the same before and after, you are going to consume some of it. You have to. And in fact, in this situation where there's no more carbon left, you can say, well, how is that possible? How would the equilibrium work if that was the case? Because carbon dioxide needs to react with carbon in order to form that. And I thought the rate of the forward and the reverse is the same. Well, it is. It just happens that that carbon monoxide, once it decomposes, almost instantaneously, you're going to flip back. So this is a really unique case when you have a very little solid, because this carbon is not going to last very long because it can react with the carbon dioxide. So over time, at equilibrium, you won't have any carbon there. Okay, I hope that was helpful. Gives you an example of how you can explain this. I'm kind of curious to see what you guys do, but I'm looking forward to it. So if there's any questions, post some questions in Google Classroom. If you see something that doesn't make any sense, also post that too, and we can continue discussing this. But if you guys can do these problems, I'm pretty certain that you can do almost any problem that comes your way. So good luck, guys.